the problem. Now, our entire system, whether the ball bot or the balancing scooter, can be modeled as a single plane of motion operating under the principles of an inverted pendulum. First, we have free body diagrams, which we use to generate our equations of motion. Shown here, we have the whole picture with the various components all attached, and then separated down into the rod and the wheel. Next, we have the sum of the forces themselves. These are broken down into the different axes of x, y, and z, with the sum of the moments about the z-axis, and the x and y functioning in the single plane that we mentioned before. This is assuming a non-slip condition, and once translated down, can become the equation of motion shown above. Now, I'm not going to go through the full details of the derivation, but after first linearizing about the zero-angle reference point, and then a Laplace transform, we arrive at the final linearized transfer function shown below. In turn, this leads us to the root locus plot shown here. As you can see, there are two open-loop poles, which stem from the transfer function itself, and then an additional zero, which comes from the controller that we plan on using. Here, this is a PD controller, which puts the zero farther to the left of the leftmost pole, which in turn provides a track for the root locus plot shown, so that both poles will be pulled onto the left half plane and create stability upon the increase of gain to the appropriate level. The PD controller itself is very simple in concept. Here is shown pseudocode for the controller as we implemented it in our code. Here we have CP and CD values that accumulate the total change we want to effect on the motor. CP comes from the proportional gain of Kp times the angle itself, or the position value of the angle, and CD equals Kd times the rate, or the velocity, more specifically angular velocity, of the machine, be it ball bot or scooter. Control in turn adds these together, and that control value is input into the motors to offset from the neutral value. While this scheme should work on its own, unfortunately we ran into problems with noise coming from our accelerometer. As such, we sought to use the gyroscope, which was integrated into the same sensor, as will be discussed later, to help smooth this out. And to accomplish this, we used a complementary filter. Here you can see a conceptual diagram of how this works, involving both the high and low pass filters that use the appropriate signals under the appropriate regimes so that we get values that are both smooth and do not have any steady state error or drift over time. The actual implementation of this filter was done using the equations shown here. PG and PA, respectively, stand for gyroscope proportion and accelerometer proportion, and must add up to equal 1. And these values in turn determine how much of the position value is set using the integral of the velocity value versus the position value itself. Having a very high gyroscope proportion makes for a much smoother signal, but introduces drift over time, which is what the accelerometer compensates for accordingly. We use different weightings between the two of these to tune for the ideal control setup. In the end, we established that 98% gyro and 2% accelerometer, or even 99% gyro and 1% accelerometer, created the best results.
We used two RS550 motors. These are 12-volt DC motors with a maximum torque output of 0.488 Newton meters. For each of these motors, we used a Bain-Botz P60 gearbox with a 64:1 gear ratio in order to achieve enough torque for balancing a person. To control the motors, we use a dual 2x32 amp motor driver. This motor driver controls both motors using simple serial communication protocol. For our sensor, we used a SparkFun 6 degrees of freedom IMU. This IMU has an ADXL 345 accelerometer that uses G-force measurement to measure angle, and it also has an ITG 3200 digital output gyro to measure angular velocity. To communicate with the sensor, we used I2C communication protocol. And finally, for our microcontroller, we used a propeller protoboard.
All right, try and go forward or backwards.
Smooth.
All right, come back forward. So much better.
That one's good.
Ooh, baby. Actually, it doesn't seem bad now that you're on it.
But you can see it is a little bit. That was me trying to go backwards.
Yeah.
That was not
It still seemed very excited about it. Yeah, you can't get the same smooth motion though.
Nope.
It is very smooth,
It's
just
very smooth, but it just won't pick you up.
but you're not actually balancing.
Well, I am. It's easy to balance just like this, and it's very smooth. But if I go at all, it gives up.
Yeah.
You know what I'm saying?
Yeah.
So. Oh. Do you guys notice the difference with no derivative?
Yeah.
It's
Well, it just looks like you're doing a lot more yourself.
yeah. Like I have to try harder. The thing is, the filter shouldn't affect this, right?
No, it shouldn't. Well, the filter just giving you a smoother accelerometer value will make the whole thing much more stable.
Yeah.
So you have more play.
Actually, it feels very, like, well damped.